Good morning, everyone. Welcome to the fourth of STAR's roadshows. We've been in Sheffield, Bristol and London, but finally we've made it north of the border to Glasgow. It's great to see you here. We've got a very varied programme this morning covering FGAS regulations, codes and standards, plant efficiency, maintenance, and then finally the growing heat pump market. There'll be a break at 10 o'clock for coffees and plenty of time for networking and chat. I think some of the badges have got, we've done the coloured spots here? No? Okay, no need to mention that. The only other messages are emergency exit is where you come in, and the toilets are just round to the right as you go out here if you feel that you need to go there at any point. So the first presentation is about FGAS regulations. My name is Andy Pearson. I'm the Group Managing Director for STAR. This is the first time I've given this presentation. Our Sales Director, Rob Lamb, is off on half-term down in England, so I'm kind of filling in for him today. So all of the good stuff is his and all of the mistakes are entirely my own. So FGAS regulations have been around since 2006. And were last revised at the end of 2014. It's about removing fluorinated gases from the atmosphere in order to reduce the global warming effect. So these gases are all measured according to their global warming potential, which is how they compare with carbon dioxide as a global warming gas. And the bigger the number, the worse it is, and you'll see various numbers thrown at you as we go through the presentation. So, first of all, the phase-down timeline, then key changes to the regulation, and then which refrigerants are worst affected by this shift in the legal requirements. We'll look at some of the replacement options that are on the table, and we'll then kind of summarise the whole picture. So this is what the European Union is planning to do with F-gases in terms of, on the side of the graph here, it's total CO2 equivalent based upon the original benchmark figure. So you can see that it goes down in steps. There's a few years of grace and then a further step. The first step has already happened, was very mild. It was a 7% reduction at the beginning of 2016. But the first major reduction comes in January next year when the level drops to 63% of the original benchmark. Now that doesn't mean that there's only 63% of the quantity of gas available. It's the quantity of gas times the global warming potential. So the trick is to move away from the substances that use high global warming potential fluids within the mixture and move towards the substances that have a lower GWP. And you can see this if you look at what the phase down means in terms of average GWP on the market. At the beginning, it equated, if you take the total number of kilograms available, it equated to GWP of 2250. R134A is probably the most common single fluid used and is about 1400. R404A is probably the most common low temperature mixture used, and it's approximately 4000. And those two are used roughly 50-50, which is why the average is round about 2000. But if we take that benchmark as 2250, if we were to use the same quantity of refrigerant as we go through the phase down, by 2019 we would need to be down at 1450. In other words, everything that we use on average would need to be about the same as R134A. That in itself is a big ask. As we progress further, by 2023 it would be down at 1000. And moving forward 700, and then finally less than 500. And there isn't a traditional refrigerant on the market that is less than 1000. So you can see the challenge is the two ways we can do this are by moving to completely different fluids that don't have a GWP, or by transferring to different fluorocarbons that have a lower GWP if we want to be doing the same amount of refrigeration. And that's really the crux of the problem. We can't just stop refrigerating things because it's absolutely essential to all aspects of all of our daily lives. So manufacturers are already developing gases that use much lower global warming potential fluids, and these things are coming on the market, but there are difficulties in transitioning and adopting these new fluids, and I'll go on to explain what those are. One of the challenges that face the high GWP gases is that the price is increasing. So you can see here the price of R404A, R134A and 407F, and it was really very stable from the beginning of the year through until May, and then we started getting these letters coming through the door saying 25% increase in the price, 50% increase in the price. I got two of these letters and I thought, oh, that one's okay, I've already seen that. But it wasn't. It was a month later, it was a second letter with the same 50% increase in price as we'd had the previous month. So the price was really rocketing at that point. It's already gone up by more than 100%. This is the price of R404A in the last 5 months. So this is presenting people with a real challenge. And the challenge is the cost of leakage is changing. You know, the mechanism is changing. Nowadays, the cost of the refrigerant is greater than the cost of 1 hour of a technician's time to go and fix the leak. So loss of refrigerant has become a really huge deal for equipment owners. And we're seeing more and more people coming to us and saying, this is intolerable, I can't run my business in this way. What can I do to avoid this problem? One of the things obviously is to really make the system leak tight. That's something that's very easy to say, but in a distributed system, particularly one that's quite old and has been in use for a long time, it's actually not that easy to do. And leakage rates have improved over the years, but they still run typically of the order of 5 to 10% of the total content of the plant every year. Another implication of high refrigerant prices is that the new investment in new plant becomes a real challenge, because if the contractor is being asked to supply the refrigerant, then the cost of the gas that's going into the plant is probably multiple times bigger than the profit that the man is going to make in the job. So if there's any issue during commissioning and a loss of refrigerant, that's his total livelihood gone. So it's actually making people reluctant to propose HFC systems because of the increased risk. So it's a real economic challenge coming in right at base level. So what does it mean in terms of the equipment that's used? Well, the regulation is very complicated, and the slides are available. I don't propose going through this in detail because each little section relates to a different person, so most of it is irrelevant to you, but there will be one line in there that's of specific importance. From a service point of view, restrictions on servicing equipment with high GWP, so that's R404A, R507, that kind of thing, they come into play from 2020 onwards, and that means that if you had a leak of that refrigerant, you would not be permitted to put the same gas back into the system, so you would need some kind of strategy to deal with that. The key thing to remember about this is it's difficult to introduce a regulation like this. It's very complicated and it needs a lot of detailed discussion. Once the regulation exists, it's very easy to change the numbers. So although it says on the slide GWP greater than or equal to 2,500, I would not be surprised if there was an amendment to the regulations in a few months or a few years' time that changes that number to 2,000 or 1,500 or 1,000. And the reason I'm confident that that's likely to happen is because it's what already happened with the CFC phase-out, and it happened again with the HCFC phase-out. The original CFC legislation from 1986 was only going to reduce the usage of CFCs to 50% of the benchmark value, and that very quickly became a total ban, and that then moved into being a ban in a much shorter timescale. So I'd be actually very surprised if these numbers do not change as we run all the way through to 2030. I think it's highly likely that they will change. So where do we go from here? We've broken it down into the high-risk fluids. If you have these fluids in your plant, then you're going to have to do something in the near future, or you run the risk of your cooling system suddenly not being available to you anymore because it can't be maintained. If you're in the middle band, then it's okay for now, but you can expect there to be something requiring to be done further down the line. And if you're using any of the refrigerants on the green side in the low or no risk, then that means that you're effectively you've inoculated yourself against the FGAS regulations. Basically, you're in a good place. And the name of the game really is to move from high risk to medium risk, or if you can, move from high or medium risk to low risk. But the further you move from the left of the slide to the right, the more difficult it is, the less familiar the plant is. So it's not possible to take an existing R404A system and put ammonia into it or put CO2 into it. You would need to make a fairly significant capital investment in plant to make that transition. So it's something that should be being planned for in the longer term, because it's going to cost money to do it, and planning for it and setting yourself up so that in the fullness of time you can meet the dates. The key message is there's not a need to rush out and do anything immediately if you're already on 134A or 407, but it's likely that in the longer term you should plan to have to do something. So one of the key things is that, as I said, moving from high to low GWP is a complex process. One of the issues is flammability. As we move from high GWP refrigerants to lower GWP refrigerants, we see the red here is highlighting the higher GWP in the left-hand column, and the green is highlighting the ones that are easier to use, what's called safety class A1. And I think David will explain more about safety classes in his presentation on standards. But you can see that moving to something like R290, that's propane. It's fantastic from a global warming point of view, but it's a highly flammable gas. It's what we use in barbecues and gas-fired heaters and so on. You can use it as a refrigerant, but you have to comply with a lot stricter regulations from a safety perspective. It gives very, very good efficiency. In small systems, it's ideal. Your refrigerator at home very probably runs on a mixture of propane and butane as the refrigerant, and it's very, very safe. It's been that way for the last 30 years. There's not any big issue of refrigerant flammability in domestic refrigerators. Refrigerators do cause a lot of domestic fires, but it's electrical problems that are the issue rather than the refrigerant itself. So propane can be used safely in small systems. It can be used safely in big air-cooled chillers that are outside in the open air. That's perfectly feasible, but it's not really appropriate for using, for example, in a split air conditioner. Likewise, ammonia, the issue with ammonia is more the toxicity of ammonia. So again, you wouldn't use ammonia in a split air conditioner, but you could use it in a large chiller system, either air-cooled chiller outdoor or water-cooled chiller within a plant room. And CO2, I'll mention a little bit more on the options in CO2. So options available for owners of existing HFC systems. You need to think about a whole bunch of things and weigh up the balance between them to figure out how you want your plant to look. Benefits of making the transition towards what are called HFO blends. These are the fluorocarbons, but with very short atmospheric life, and therefore they don't have a big impact on global warming because they don't last long enough to have a big impact. They decay into other compounds. They're designed for the application. They're much more similar. You can use copper piping of the same pressure ratings. You can use similar kind of compressors, semi-hermetics and so on. Using HFOs can get you down to GWPs in single digits for the direct effect of the GWP. The challenges are, if you think that 404A is expensive, you haven't seen these guys yet, because one of the reasons that the price is increasing so rapidly for the HFCs is kind of managing the expectation gap. At the moment, R1234YF, which is the refrigerant used in car air conditioning from 2017 onwards, is £75 a kilo, and price likely to go up rather than down. That kind of sets the benchmark for these. So the days of buying refrigerant at £2, £3, £4, £5 a kilo for the stuff that goes in your air conditioning are kind of gone. You know, we're headed more towards the double-digit, possibly even triple-digit per kilogram refrigerant costs. That's why I say it's more expensive than an hour of the engineer's time servicing the plant. They are low GWP, but a lot of them are also mildly flammable. And again, David will explain more about what mildly flammable means in his presentation. Many of them also have a big temperature glide. The temperature changes as the refrigerant evaporates. Now, we're used to that now because R407 in its various flavours does that, but you need to design for it. So a 404A plant won't necessarily work as well or as efficiently with a 448 or 449 plant with a bigger glide. And And there's loads to choose from. It really is genuinely very confusing to figure out what the best bet is. Refrigerant cost is really the big negative, and the others are... the green, amber, red here really means not an issue, a little issue, a big issue. It doesn't mean you can't do it, it just means you've got to think about it. So if we move on, carbon dioxide, not used as a refrigerant at all in the 1980s, used as a refrigerant in the 1880s. So the technology has been there a long time ago. It went away, and since the early 1990s it's been coming back again. It's been adopted quite widely for supermarkets. This shows two types of carbon dioxide system, one rejecting heat to atmosphere above the critical temperature, the other one a pumped circulation system with an R134A high side. Benefits of CO2, it's by definition GWP1, it's A1 safety class, and it's very low refrigerant cost. It's back down to the single digit pounds per kilogram. The challenges are it runs at high pressure, and I always say to people, don't knock the high pressure, because that brings you all the good stuff about CO2 as well. So it's actually a benefit, not a disadvantage, but I would say it's a consideration is the key thing. And there has to be a question mark over the life of these systems just because they haven't been around as long as the others. I'm confident that a CO2 system built for industrial purposes will last as long as any other industrial system. The first one installed by Star was put in 1999, and the equipment is plenty strong. You know, it's as good as an ammonia system and can be in service for 20, 30, 40 years. Most of the CO2 systems in the UK have been employed in the supermarket arena, and they tend to be switched out more frequently, so we don't actually have a big track record of long life of CO2 systems of that type. So CO2, you can see, is mainly green, but the materials of construction are different, and it's not possible to retrofit. That's the key message. If we look at ammonia systems for industrial refrigeration, it's become the go-to refrigerant. And what's changed in ammonia is we don't build systems the way we did 50 years ago. We're now very focused on building low-charge ammonia systems. So this shows what is in effect an ammonia condensing unit attached to a cold store. Very low charge of ammonia. It's all outside the building except for the evaporator at low pressure inside. It's factory built, able to be deployed on site very quickly. No cost for building an ammonia compliant machinery room. So a very cost-effective way to switch if you're doing industrial type refrigeration. Ammonia is the only refrigerant on the table with zero GWP, and it's been used since the 1850s, so there's a huge wealth of experience in using ammonia as a refrigerant. Very, very low cost per kilogram and very widely available because it's mainly used in agriculture, and use of ammonia as a refrigerant is a tiny proportion of the total ammonia production in the world. So widely available, cheap and easy to use. The challenges are the equipment and installation costs are likely to be higher. It requires a higher degree of training for operators, and it is a toxic gas, so you need to pay attention to safety analysis. And again, David will reference that as well. And you can see with ammonia, low GWP, flammability a minor issue, toxicity a major issue, and again retrofit not really feasible. And then moving on to hydrocarbons, I mentioned already, widely used in domestic refrigerators and in some chillers. You can see there the benefits are low GWP and non-toxic, but the flammability is a big consideration, unlike ammonia, which as I said was a more minor consideration. And again, retrofit probably not feasible into an existing air conditioning system. So in summary, prices are going up very, very rapidly, and we don't know where they're going to finish, and availability will be constrained in that respect. There isn't a single solution, but new solutions are required. There are plenty of options and opportunities to do things, so it's not a case of being corralled down a single track, but in some ways that's a disadvantage because it makes it quite confusing. We're seeing a big growth in the use of CO2 and ammonia, and they're moving into areas that they wouldn't have been used before. Chillers for building services, for example, or CO2 in freezer plant where it gives excellent performance, very high efficiency. So there are benefits to be had by making these transitions as well. You can convert your plant and make it more efficient than it was before with a judicious choice of gas. And finally, if you want more information, Don't ask me, ask Rob Lamb. So that's his contact details. Thank you for your attention. We'll take questions at the end of the first session. So David's going to talk a bit about codes and standards now, and then I'll come back and talk a bit more about efficiency. I'm handing over to him 3 minutes late, but I'm sure he'll do the same to me. So thank you very much.